Now we are going to do more combination of the sine and the cosine function, but not ones that we can just take out from the chart. Here is the first example, and also this is the finite integral. It's pretty clear that u has to be sine x because it is a composite function. It's 1 over radical of the function sine of x, but also it's going to work really nice with the cosine because du is cosine x dx. So as you can see, now I split the exponent to cosine to the power of 2 of x, which is even, excellent. So I will be able to express this as sine x without radicals, and cosine x dx, which is just the du. So I get that because cosine to the power of 2x is 1 minus sine to the power of 2x, which is 1 minus u to the power of 2. Don't forget to change the limits of the integration. Sine of pi over 2 is 1, so the upper limit is u equals 1, and the lower limit is u equals 1/2 because sine of pi over 6 is 1/2. So now this is a pretty simple integral, just that the algebra here is a little bit messy. We have to distribute the radical of u, and we get that. So here is the antiderivative. Let's simplify a little bit. Okay, we have 1 over 2 in the denominator, then we have 5 over 2, which is actually multiplying by 2. So we get that. And now we're going to substitute 1, and we are going to substitute 1 over 2. Okay, don't forget, exponent of 1/2 is the square root of. And we can simplify a little bit the algebra to get that. Here is another example that the chart really is not going to help us to do. Really tempting to take cosine x to be the u, but this is wrong because if you take cosine x to be the u, then sine x dx is the du, but what about the 1 dx? This cannot be expressed as something of the cosine function. Why not just distribute cosine x, and then we get secant x and tangent x. And here's the antiderivative. We want to manipulate a little bit this antiderivative before we are substituting the limits of the integration here. So first we use rule of logarithm, so we get that this is ln of the first one over the second one because you have minus. Now we want to simplify that, so secant x over secant x is 1, and we get also tangent x over secant x that we would like to simplify right now. We express everything as cosine and sine, and we figure out very quickly that this is just sine of x. First we plug pi over 4, and then we plug 0. I would like to recall sine of 0 is 0. Okay, and sine of pi over 4 is 1 over radical 2. So we just get this one, but now I observe that ln of 1 is 0, so I get that. This is not the only way to evaluate this integral. Actually, it's a little bit dangerous to do exactly what I just did, because then you really have to memorize what is the antiderivative of the secant x, which is not very trivial. Now I'm going to do the indefinite integral of the previous example in 2 different ways, which make more sense, because then I don't have to remember what is the antiderivative of the secant x. What I'm going to do, I'm going to multiply both the numerator and the denominator by cosine x, and see what I'm getting here. I'm getting that, and this is wonderful. Why this is wonderful, you ask? Okay, so first of all, cosine x dx really pops out to be the du. And then I have cosine to the power of 2x in the denominator, which can be easily expressed as 1 minus sine to the power of 2x. So what is the big deal? You will see in a second. Now you should observe that 1 minus sine to the power of 2x is 1 minus sine x times 1 plus sine x. So actually, you end up with that. So now, we should do some u substitution. The question is, what is the u? One thing is clear, it has to be or sine x or 1 plus sine x. Well, obviously it's going to be 1 plus sine of x, because if I will just have a u substitution for the sine x, I have no idea what to do with this plus 1. Also, on the other hand, the du is not affected by taking 1 plus, because the differential of 1 is 0. So now I just get the integral of du over u, which is ln of u in absolute value plus c, and the only thing left to do is to substitute the 1 plus sine x instead of du, and I get that. So now I'm going to do it in a different way. Now I'm going to multiply top and bottom of this function by the conjugate of 1 minus sine x. And see what I get now. I get that. But then I realize that 1 minus sine to the power of 2x is cosine to the power of 2x. So I can cancel out the cosine x. And I get that. So what this is good about? Oh, well, the du is really popping out. The du has to be cosine x dx. And the u is 1 plus sine x. And I get exactly as before. I get that, and I get that. So I showed you how to do it in 3 ways. The first one was if you have really good memory, but if you need to show everything from scratch, you really prefer the other 2 ways, which are really more or less really the same. Trigonometric integrals with mixed angles. Here are some identities to transfer a product of mixed angles to a sum. Here is the first one. Second one. And here's another useful one. It's not definitely easy to remember that, okay? But if you do, it will make an integral of the form sine of a cosine b, or sine a sine b, or cosine a times cosine b, very easy integral. Because to integrate the function on the right in those 3 cases, it's very easy. Pay attention that this is not the only way to integrate the product of mixed angles. Another way is also integration by parts, as we are going to show later. A very special case of that is when a equals b. Then we get the double angle identities. Sine of 2x equals 2 sine x cosine x. And cosine 2x can be written in 3 different ways. Cosine to the power of 2x minus sine to the power of 2x. It's also 2 cosine to the power of 2x minus 1. And it is also 1 minus 2 sine to the power of 2x. It is both to memorize sine of 2x and cosine 2x identities here. So let's do an example. So you can see that we have 4x here as the angle, and here we have 3x, so we have to use one of the identities, and it's exactly this, because we have sine of something times sine of something else. So a is 4x and b is 3x. So cosine of a minus b is x, and a plus b is 7x. And this is very easy integration. I'm not even going to show you the step. The first one is just the direct integration of cosine x. The second one is a small u substitution when u equals 7x. Another example. Here we have a combination of 10x and 20x. So again, we are going now to use this. Okay, so a minus b is now minus 10x, and a plus b is 30x. Okay. And I want to recall that cosine is an even function, so to integrate cosine 10x or integrating cosine negative 10x is exactly the same, so why not to integrate cosine of 10x? Okay. And we get that, and now we have to do twice very simple u substitution. For the first one, u is 10x, and for the second one, u is 30x. And again, you can always differentiate and check if everything is right. Let's now integrate sine 2x times cosine x dx. One way of doing it is really to use that. Okay, so a is 2x and x is the b. Okay, and we get that. And again, a very simple u substitution for the second one, when u equals 3x, will give me this antiderivative. But also there is a different way. We have here sine of 2x. This is definitely the way I'm going to do it if I have an exam and I'm not giving all those sophisticated, very difficult to memorize identities. But it is really recommended that in Calculus 2 everybody will know what is sine of 2x. It's just very useful. So sine of 2x, it's 2 sine of x cosine x. So I can write this like this. Now I observe that I have a trigonometric integral directly from the chart. We have a combination of cosine to an even exponent times sine to an odd exponent, okay, because it's a power of 1. And now I know exactly what to do. I know that the du is going to be negative sine x dx, and du is cosine x. So I write it like this. And I get just this is negative 2 integral of u to the power of 2 du, which is just that. And now we are going to replace u by the cosine x, and we get that. These integrals can also be evaluated by integration by parts twice, because the integrands are products of two loopy functions. For example, we are going to redo the last example using integration by parts twice. Here is the first time. As you can see, we chose u to be sine of 2x and dv to be cosine x dx. We are getting that. Now let's focus on the second integral. We will apply again integration by parts. We have to be consistent, so now the u is going to be cosine of 2x and dv is sine x dx. We are getting this. Now let's distribute and simplify. Let's now pay attention. We get that 1 time our integral equals sine of 2x times sine x plus 2 cosine 2x times cosine x plus 4 times our integral. As usual, we are going to do some algebra. We get that negative 3 times our integral is sine of 2x times sine x plus 2 cosine 2x times cosine x. We divide everything by minus 3. And we get our integral. Even though the answer looks different than before, this is exactly the same.